All right, gang, Math 6610, more on categorical analysis. Well, I can't stress in education research how important it is to be able to understand how to handle categorical data, categorical information on students and schools and instruction and so on and so forth. It seems like that so many studies that we conducted in education that are geared toward improving instruction or programs deals with success, and oftentimes we dichotomize success as C or higher, and a non-success would be maybe D or lower. We also run into situations where if we want to investigate instructional techniques, we get into experimental control groups. And sometimes we want to look at instruction across maybe day and evening courses, maybe courses taught by adjuncts and full-time professors, tenured professors. There's all kinds of ways that we can dichotomize and categorize information in the education world. So it's important to understand the limitations on categorical analysis as we currently have seen them, and know what to do about that. So first thing that I kind of want to put on your radar is when we have two quantitative variables, and we'd like to examine the relationship between these two variables. So, for example, maybe we want to take a look at the student's ACT math subscore and look at their GPA, their first semester in college or their first year, however the population is being defined. Because we have two quantitative variables here, what we would probably look at is we'd probably look at the correlation. And we've already seen in this class where we have a quantitative variable meets a categorical. Now, if our categorical variable is divided into two groups, I think the classic example of that would be male-female. Let me get, there we go. Then we would do a two-sample problem. We'd have a two-sample situation. So we'd probably conduct a two-sample t-test if we wanted to test the equality of the group means across two groups. So, for example, if we wanted to see at Shawnee State University if there's a difference in mean ACT scores across gender, then we would certainly want to do a two-sample t-test. And just recently, before posting this video, I'm pretty sure, we studied ANOVA. And ANOVA is the same thing. We have a quantitative variable, and it meets a categorical variable where we have more than two groups, so 3, 4, 5, whatever it may be. So K is 3 or higher. So, but what I want to focus on in this video is just, how do we examine the relationship between categorical variables. Now, people that are at kind of in the early stages of this, you ask just about any first-year graduate student that's entering into education research, how would you, what statistical procedure is important, or not important, but appropriate to examine the relationship between two categorical variables. For example, what if we wanted to look at a relationship between success rates across professors? So we have example, we may have two professors. We'll call them Professor A and Professor B, and we'll just call our success rates coded as zeros and ones, where zero is non-success, and we can define success however we feel is appropriate for the study. We just have to obviously tell the audience, tell the reader that, and then let's say that one is success. So let's just say this is non-success, and yep, the student actually succeeded. Now, guys, I have a data set. Actually, I have a couple of data sets that I want to I want to show you. The first one that what I'd like to do is just examine the relationship in this hypothetical data set between success rates across professors. And I want to take you through a process of, first of all, finding the chi-square, or conducting a chi-square and finding the chi-square statistic and the p-value, and pointing out to you that once we carry out that process, we really don't know much. In fact, I think it was Sir Austin Bradford Hill, and some people say it was even Tukey that say, like fire, the chi-square statistic is an excellent server, but a bad master. It really just doesn't tell us much. So what do we do that actually does tell us much, or important information? Well, I'm going to take you through that process. Okay. Now, the very first thing that I would want to do here is that I'm going to go split screen on you. I should have already had this up, but for some reason I didn't. Oh wow, what's going on here? They want me to check for all sorts of updates, and I don't want to check for updates. I just want a nice, leave me alone. All right, let's get this large enough where you guys can see it. Or better yet, let's get it large enough where I can see it. So what I want to do is I want to carry out, set up this data set for this. Now, what you may want to do is, and I've seen people do this, is let's just call the first, Prof A success, and then let's go Prof A non-success, and the Prof B success, and the Prof B non-success. All right, so the Prof A success, we can see that we need 22 of those, so I'm just going to come in with a yes here. No, where did I come up with 22? We need 28 of those, so I need to come down to the 29th. I'm losing my mind, people. All right, so I have yes of those, and it looks like Professor A has 10 non-successes. All right, Professor BS had a few of those before, haven't we? Professor B success is 48. Hopefully you're not saying that about Darbro when it's all said and done. If you do, just don't tell me. So what do we say? 48 of those, so we need to come down to 49. And Professor B NS, I'm not going to say it. I want to. So we're going to say no. So we need to come down to the 115th line. All right, guys. Now, if you want to really screw up, leave your data set like this, import it into R. It's just not going to work. What I want to do is I want to come in here and insert a couple of columns. And I have to set this data set up appropriately. I have two variables here. The professor and success, yes or no. So what I can do is I can come in here and say that these yeses, I'm going to copy those, go with Professor A. Well, and I can just go ahead and say that these no's go with Professor A. I found it easier to type these out in columns because it's sometimes it's kind of tricky. And you know, if you watch this and you're like, I don't like the way you did that, well, do it your way. It's not like I'm going to be there watching you or anything. Professor BNS, Professor B. I'm dying to say it, but I'm not going to. My preacher may be listening. was giving Taylor Swift a hard time in one of my undergrad videos the other day, so I woke up a cold sweat worrying that she may be watching my videos. All right, gang, the first are go with A, the first yeses and nos. And the others go with B. So always remember that your data set in the end needs individual information on the rows and variables in the columns. Last time I taught 6610 was last fall, and the first assignment, the people who screwed up the most were the ones who would leave the data set in this situation right here, and then they'd use the commands that I teach them in these videos, and it didn't work. And they're emailing me or calling me or texting me, whatever it may be, at 10, 11 o'clock the night before this is due, and I'm like, dude, watch the videos. So let's just save as. I'm going to be very creative here and just call this success. Go to the desktop, and gang, we need to save it as .csv. You can actually use Excel format to get information into R, but I have found that that this is the most. It just seems like it's the most seamless way to get a data set into R. All right, gang, we should be pros at this by now. Let's set our working directory. Now let's go get our data. We, of course, have to attach our data if we want to make anything happen. And then I just like to look at the names of the data to get this going. Now, to conduct a Chi-square in this format, the first thing we need to do is set up a table. And what I want to do here is use what's called X tabs. And I use a tilde. And then I put in the variable first that I want on the rows. So I'm going to try to simulate the table that I have on the handout over here. Prof. Okay, so I can look at table, and you can see that we get the same counts, or do we? 48 students succeeded. Actually, that's kind of weird. Did I name that the wrong thing? I think I did. Let's just look at our data. I think I named. Well, shoot. Guys, that's horrible. That's going to drive me absolutely insane. But, daggone it. All right, let's, well, how can we do this? Let's, shoot. I'm not starting this video over. I've got too much going on. Let's get out of this. I can't stand that. Sorry, guys. It's just a weird the way I am. I mean, I'm sure it would have been fine, but I just can't handle that. You ever have this happen in your class? Probably not. You're probably sitting there, no, never have. All right, gang. That's going to be much better. All right, so let's go through this stuff again. Okay. Shoot. See, that's the thing about teaching in class is I would have had some student that would have said, Dr. Darbo, don't you think that professor should go over in the column that it needs to go in instead of backwards like you did it? All right, gang, let's create the table just as we did before. Hopefully it It works out correctly this time. I want success on my rows and prof on my columns. So we can see our table. We get this. Thank goodness. All right, so we have Professor A who has 28 successes and 10 non-successes. Now, let's let's go ahead and set up the chi-square. Now, the first thing we have to do to use there's a command called cross table, and we have to get a package installed before we can do that. So I'm going to go install packages, and we need gmodels installed before we can do what I need to do. So guys, always go to USA, California 2. That's the UCLA folks. I like them. I've never met them, but I think they do. Well, let's just put it this way, it works. And then let's access the library for gmodels, and life is good. All right, now, I don't know if life is good, but we're going to use what's called a cross table command, and I'm going to implement this on table. And first thing I want to do is Fisher equal true. Now this is going to give me my odds ratio. And there's a little trickiness here on the odds ratio because the odds ratio that we create by hand may not be the one that the R gives us because of some things that I'll point out. It's going to give us either what we want or the inverse because it could do the odds of non-success when we actually look at the odds of success. But I'll talk about that in just a second. Let's, next thing, is that right? Chi-square, yeah. Equal true. This will give us our chi-square statistic and p-value, which is a good place to begin, but it's certainly not the cure-all. We want our expected values, obviously. I definitely want my standardized residuals. And finally, we want the type to be either SPSS or SAS. Now, oh shoot, I hate it when that happens. No, okay, that's my bad. This is why I should use notes when I teach, but I don't, so be it. So instead of, I did that kind of quickly, instead of type, that should be format. Okay? Now, SPSS and SAS, the other option there is to use SAS. I forget exactly what the difference is. I don't remember. I'd have to look that up, but I just remember that I always choose SPSS there because it gives me the output that I want. Now, you can see that in each cell, what we get are these 7 things. And when I'm looking at something like this, the very first thing that I am going to want to do is go to the chi-square statistic. Now, when I look at this, I get 2 things. I get a Pearson chi-square, and I get a Pearson chi-square with Yates continuity correction. It's my opinion that when you have a 2x2 table, that the chi-square statistic is slightly overinflated. So to correct for that, and again, this is when you have a 2x2 table. So when you have a 2x2 table, which we clearly do here because we have success over professor, and each of these are divided into 2 subcategories, if you will. I would report the Yates continuity correction. Now, if I have a 2x3 table, and I'm going to illustrate that later, I would not. So if I'm going to report this, I would say that our chi-square with degrees of freedom 1 is 23.52. And then I report the lowest level of significance at which my p-value falls below. So again, those are 0.001 is the lowest level of statistical significance, 0.01 is the next, 0.05 is the next, and if we get a p-value above 0.05, then we just report it. Now, so guys, I've got this output from our chi-square statistic. So when I consider that the null hypothesis is that success and professor are independent, in other words, not related, versus the alternative, this is just not my day, is it? Success and professor are dependent, in other words, related. So because my p-value is less than 0.05, the game that we'll play here is we'll reject the null hypothesis, and usually we don't get that dramatic and draw lines through it, but based on the data that we've collected, it's more believable that success and professor are dependent. Okay? Now, what do we really know? Well, we know that the p-value is relatively small, and many would conclude that there is some association between professor and success. Okay, it's fair enough. But does the chi-square really tell us what we seek to find? And what we really want to know is what is the nature of the relationship between Professor A and Professor B. Now, you can examine this data set and without any fancy-smancy statistics, and you can just look and see that 28 out of 38 students for Professor A succeeded, while only 48 out of, 162 succeeded for Professor B. So you can eyeball this and get a decent indication. But guys, anyway, at the end of the day, the chi-square value tells us very little and is considered by many statisticians, myself included, not that the statistics world is sitting on the edge of their seat waiting to hear what I have to say, but by many statisticians to be an overused, an oversimplified method of evaluating the relationship between two categorical variables. So what should we do? How do we do it right? Well, guys, again, always begin by reporting the chi-square statistic and see what happens. But the next thing I'd want to do, so let's just going to be a next in a string of many next, is I would examine the standardized residuals. And we're kind of lucky here that R gives us those. And so let me bring this up. And what I have as my tunnel vision, first of all, I need to find out where it is. So up here it gives you the legend. So it tells me that each of those is the last entry in each cell. So what I tend to look at here is that any standardized residual between -2 and +2, I don't find that interesting. It's the ones above +2 and the ones below -2 that I tend to focus on. So when I see this, I'm just going to tell you about the 3.568. This tells me that the observed frequency of students who succeeded under Professor A is 3.568 standard errors higher, because it's positive, than expected under the null hypothesis. Now you guys got to remember, the null hypothesis state that there's no relationship. So if there's truly no relationship between success rate and professors, that cell count is 3.568 standard errors higher than we would have expected if there was no relationship between professor and success. So that gets us a little bit better. than just the chi-square statistic. And we're going to, again, improve on this at each and every step. The negative 2.794 tells us that the observed frequency for those who did not succeed under Professor A was 2.8 standard errors lower than we would expect if there's no significant relationship between success and professor. So that's cool. That's good. I think we covered that in the previous video, but I want to, something that really kind of, I'll just go ahead and put it out there, kind of pisses me off when I'm working with students in the students in our program who are going through the entire program, and they come up and they're doing their research, and they come up to a situation where they've got to analyze categorical variables, and they go out there and start looking at Googling it. Guys, I'm telling you everything you need to know. If there's anything else we need to know, we'll talk about it. We'll figure it out at that time. So when you, a year from now, or whenever it may be, you're working on your master's thesis, again, if you do decide to complete the entire program, just go back and look at these videos. I'm telling you what you need to know. Okay? Now, the next thing we need to do, and I'm just going to put this in as number 2, and it's going to really help if you can take a look at this as I'm writing. The second thing is we want to get into measuring the strength of the association. Now, the most straightforward way that I know to measure the strength of the relationship is just to compare proportions. So under Professor A, the percentage, let me get my data set that, and I want to get a calculator. So guys, hold on, I'm going to grab a calculator. All right, gang, so looking at proportions, we can see that Professor A, that 28 out of the 38 students, my mental math tells me that that's 0.74, but I'm going to check this out. Yeah, 0.74. And Professor B, we get what, 48 out of 162. I get about 0.3 something there. So what do we get? 0.30. Huh. My mental arithmetic usually doesn't work that well. So we can compare proportions. And comparing proportions requires you to be able to carry out a very highly sophisticated arithmetic operation called subtraction. Guys, I'm sorry. I know that's very difficult, but we can get through this together. So we get a difference in proportion of 0.44. Now, the cool thing about this is these differences in proportions will always fall between -1 and +1, which to me is really cool because this is the range of outputs for the correlation coefficient R if we're examining the relationship between two categorical variables. So what we can say is this 0.44 falls about right there, telling me that we have a moderate association between the difference of relationships between Professor A and Professor B, depending on what we already know about correlation coefficients. Remember, as R's get closer and closer to +1 and -1, it indicates a stronger relationship, just, a positive relationship versus a negative relationship. All right? Guys, we're getting ready to get to the good stuff, okay? As interesting as comparing proportions may be, we need more. And the next thing that I would want you to be able to do if you're examining the relationship between categorical variables is to come up with what's called the odds and the odds ratio. Now, let me show you some things that I've already done here, and I've jotted these down, so let me make sure that I get this correct. Let's look at the first situation, and what I've done is I've just created a contingency table, and I've just put in some stuff. These numbers, all right? So I've got a sample size of 200, and I ran the chi-square on this, and the chi-square statistic on this was about 0.08, and the p-value was very high. No relationship between, let's just call it categorical variable A and categorical variable B. But if we look at the difference of proportions, we have 51 divided by 100 minus 49 divided by 100. We get 0.02. All right? Let's keep the stuff similar, but let's double it. Okay, so that's going to be 102. This is going to be 102. This is going to be 98. Okay, so what we have is we have 400 subjects. The chi-square, which I ran earlier, turns out to be chi-square statistic is 0.16. Our p-value lowered to 0.69. Notice that the relationship, the difference of proportions, is still 0.02. The third one I want you to look at, I bumped this up by 100. So I have 20,000 subjects. Still, our difference in proportions is 0.02, but my chi-square statistic was 8, and my p-value was 0.005, which is statistically significant at the 0.1 level. Now, let's examine the odds ratio. Now, the odds and odds ratio are very easy to find. What we can do here is the odds, if we just look across here, would be 49 over 51, which we take in, of course, obviously in odds. I don't need to go through that at the graduate level, but odds versus probability is just the number of let's just call it successes, quote unquote, versus the number of non-successes. So we're looking at essentially a 0.96, and then as 51 divided by 49, we have a 1.04. So the odds ratio is going to be the 0.96 divided by the 1.04. So we get about 0.92. I tell you what, I'm not real happy with that. So let's go 49 divided by 51 divided by 51 divided by 49. Yeah, 0.92. Well, if we look at this, we're going to get 98 divided by 102 divided by 102, and you know what's going to happen, just like I do. The odds ratio is 0.92, and the odds ratio down here is also 0.92. So my point is the statistical significance clearly doesn't tell everything, because the difference of proportion can remain stable and the odds ratio can remain stable, yet we can lose our minds down here thinking that we have this significant association just because our p-value was inflated by extreme power. We have a lot of power here because we have a very, very large sample size. So guys, I think about it, we need more stable measures of the strength of the association that aren't as contingent and a function of increasing the sample size. Now, here's what we end up with. We end up with a situation where when we look at the odds ratio, and let's go back to Professor A and Professor B, and we have Professor A and Professor B, and we have success and non-success. So we have, what, 28 to 10 and 48 to 114. So what I can look at in this situation is, first of all, I could look at the, well, let's go this way. I could look at the success for Professor A. So 28 divided by 10, 2.8. So a student in Professor A's class is 2.8 times more likely to succeed than not succeed. Professor B doesn't fare quite as well. In fact, it's kind of almost a pathetic success rate of 0.42. So I like to think, to me, odds are more difficult to interpret when they're less than 1. So what I would probably be more tempted to think about here is the 114 out of 48, which is 2.4 times. So we can say that students are 2.4 times more likely to not succeed than succeed. Nevertheless, in comparing the odds ratio, we have to keep it consistent for success. I think of this kind of when you guys teach logarithms and exponents. Exponential form and logarithmic form. You know, I've done logarithmic form long enough to where I'm comfortable with it, as we all are, but some of my students aren't. And I kind of tell them, you know, that's kind of like a second language. Logarithmic form, when you're learning these things, comes a lot easier if you'll think about it in exponential form, because that's something you're more familiar with. It's kind of like a second language. If you have a second language and you go to a country that primarily speaks that language, you're still going to think about things in your first language and then translate it to the second language. So this is kind of a second language here. Anytime I get an odds ratio below 1, I think about it this way. So guys, in the odds ratio here, what we actually end up with is we end up with kind of the center value of 1. So that would be that the odds are equally likely, down to 0 up to positive infinity. So we can kind of think of this range of outputs as kind of a right skewed distribution. So the point, you know, just for example, let's just concentrate on just Professor A. The odds of success, as we saw, were equal to 2.8. The odds of non-success are 10 divided by 2.8, or I'm sorry, 10 divided by 28, which is 0.36. So we have 0.36 and 2.8. These values aren't centered around the number 1. So what we'd like to do is we'd like to create a distribution that is centered. And what we can do, and we found out that we can take the natural log of the odds ratio. I'm sorry, take the natural log of the odds, and we get something that is centered around 0. Now let me show you what I mean by that. Let's go back to the illustration of Professor A. If we take the natural log of 2.8, we get 1.03. If we take the natural log of 0.36, we get negative 1.03. Now guys, remember the 0.36 is just 10 over 28, and this is just 28 over 10. So by taking the natural log, we end up getting a distribution, well not a distribution, but a range of outputs that are centered around 0, thinking of like a mean of 0, whereas up here we have a range of outputs that are positively skewed. Well guys, that leads us into what we would do next. So let's get a little bit of notation. So let's let theta hat equal our odds ratio. So in our situation, the odds ratio for success from Professor A to Professor B. So 28 to 10 for Professor A, and 48 to 114 for Professor B. So guys, let me pop that in the calculator. We get an odds ratio of 6.65. So for our problem here, this turns out to be our theta hat. Now the next thing we'd want to look at probably is the natural log of our theta hat. Which is 1.89. Now, this tells us that the odds of success for a student in Professor A's class is 6.65 times higher the odds of success for a student in Professor B's class. Now, I don't know what's up with this professor. Trust me, we've had this before at Shawnee State. We had a professor that was with us a few years ago that taught a developmental course one semester, and I got pulled into it because I was the developmental math coordinator at the time. But this person started out with 34 students. He or she, I'm not going to tell the gender, he or she gave 31 Fs, 2 D pluses, and 1 C minus. And they blamed the students. Okay. To me, that's kind of like being a medical doctor and looking up and all your patients are dying. Maybe you need to consider a new profession. All right, gang, enough of that. What we're going to do next is we're going to take this odds ratio and we're going to look at what's called an inference procedure. And ultimately, the inference procedure addresses the question, is our odds ratio statistically significant? Now guys, at this stage of your career, I don't know yet whether this is natural, But when we talk about statistical significance, I mean, essentially what we're talking about here is we need to come up with some test statistic that creates a p-value, and we play this silly game. If our p-value is less than 0.05, we get statistical significance, and we get earth-shattering, groundbreaking news that we can go headline, headlines with, breaking headlines. Uh, by the time you finish this class, you're going to not have a lot of faith in that procedure because I'm going to point out a lot of flaws to it. But nevertheless, it's the game that's played. So, what all do we need to be able to calculate a test statistic and a p-value? Well, the first thing we got to have is we got to have what distribution, what probability distribution models this phenomena. What probability distribution are we drawing from uh, to, to calculate this p-value? And once we decide the distribution, we have to find out the parameters. What's the spread? What's the center? Well, it turns out in this situation, we model this with a z distribution, which is a normal distribution, mean 0, standard deviation 1, and the standard error of this odds ratio is just the square root of 1 over a plus 1 over b plus 1 over c plus 1 over d, where a, b, c, and d are just the cell counts of our 2 by 2 table. Okay? So for our situation, we get, I don't know why I keep losing my table. Here it is, right here. So for our situation, our standard error for the natural log of our odds ratio. And actually, I think, you know what, guys, I think I misspoke back here. I did. That was bad. This is the standard error for the natural log of the odds. So we found the odds. We calculate the odds ratio, and for reasons that I explained before, we take the natural log of the odds ratio, and that's our focus because we end up with a centered distribution. So the standard error here would be the square root of 1 over 10 plus 1 over 28 plus 1 over 48 plus 1 over 14, which is going to be super easy to find. So our standard error would be 0.407. Now, next thing we do is we calculate our test statistic. And the test statistic obviously follows the z distribution, so it's z equal. And our estimate is the natural log of the odds ratio minus the mean, which is 0, over the standard error. So gang, the natural log of our odds ratio would be the natural log of 6.65 over approximately 0.407. Now this is actually, I can go ahead and tell you, this is not going to work out really well. I guess it's fine. But 6.65 was the odds, right? Not the odds ratio. I'm sorry, the odds ratio, but not the natural log. Yeah. Yeah, natural log of odds, yeah. So 6.65. Or I think it was 1.89 divided by 4.407. So we get about a 4 point, let's just call it a 4.65. It's going to be close enough for comfort. So guys, what we know now is we know that this is modeled by the z distribution. Mean zero, and standard error, as I said. So standard deviation in the z distribution is typically 1, but there's modification for the odds ratio here. So our standard error, based on this sample size, will be 0.407. So to calculate the p-value, we're going to conduct two tails. So we're going to look at the area to the right of 4.65 and to the area to the left of negative 4.65. Okay? Now, in either situation, we can calculate the p-value here. Now, what we're going to use is in R, there's something called p-norm. And what this will have you do to put in your test statistic and your mean and your standard deviation. Now, obviously, we have sample issues or sample size involved, so we have our standard error that will go there. So anyway, whatever we put right here, this R command will calculate the area below. So if I would happen to put in 4.65 here, it's going to calculate all this area here, so I would have to go 1 minus if I put 4.65 there. But you can see if I put negative 4.65, I'm going to be fine. So I would just need to take 2 because I have 2 areas. P norm, negative 4.665, mean is 0, and our standard error was 0.407. So we're going to get a rather low p-value here. So let's take a look at this. All right, so we get an extremely low p-value, which is statistically significant at the 0.001 level. You can see there we have negative e to the negative 30, which is an extremely small value. Now, kind of as a rule of thumb, what you can think is anytime you get your test statistic that we had before, anything greater than 2 is typically an indication that you're going to have statistical significance. Okay. Now, one more thing to think about. Let me go ahead and just finish this up. What we can conclude is that the relationship, that the result here is statistically significant. So there's definitely something going on of value in the difference in success rates across professors. In fact, the odds ratio tells us a lot of information there. Now, how would we write this up? What I did, I just went ahead and wrote it up, and I'll just put this here, and you can do a screenshot on this. So let me go ahead and get this large where you can see it. What I would do, and I hope you guys can see that. Let me see if it's. Well, if not, I'll read it to you. I said there's a statistically significant relationship between grade and professor. Actually, should be success and professor. Chi-square. Actually, I think I reported the chi-square statistic here, and not the Yates. So I would report the Yates correction. But our p-value was less than 0.001. I don't think that's right, is it? I think I've lost my mind here. Yeah, it is. And 23.36. So guys, I made a mistake there. I would report the Yates continuity correction 23.52 because we have a 2 by 2 table. Clearly we are less than 0.01, and the odds ratio was 6.58. Guys, I'm going to show you guys how to come up with this this confidence interval in a future video. What you can do is you can come back to your output, and you actually get an odds ratio. It's probably not going to be the right one. The Fishers, when we said Fisher equal true, this right here gives you the sample odds ratio. Now you look at that 0.1519 and you're wondering, well, why is that not what we got? Well, guys, if you take the inverse, 1 divided by 6.58, you'll see that you get the 0.15. So it calculated the odds ratio on non-success. So the odds of non-success in Professor A's class is 0.15 times the odds of non-success in Professor B's. There's a way that you can force this to look at success as your baseline. I don't remember what it is right now, but how to do that. But I mean, that's just one of those things you just look up and report it and go on with your life. Guys, I've lost my data set again. Let me show you what we would do. I want to show you a little bit more of a sophisticated example. Yeah, here we go. You know, what would happen in the second example here? What if we had a situation where we don't have a 2 by 2? So what I want to do is just concentrate on this one right here. What would we do there? Well, I've kind of already gone ahead and done this for you, and I'm not going to show you all the calculations, but you can test them out for me. What I would do there is I would clearly set up a data set just like I did before, and bump it into R and calculate the chi-square and so on and so forth. But from there, I'd follow the same thing. I would look at the chi-square statistic, report statistical significance if it's achieved, get into comparing proportions, get into odds ratios, natural log of odds ratios for all of the pairwise comparisons. So, guys, ultimately what you would end up with is something like this. You would end up with, let's go Professor A to C comparison, Professor A to B comparison, and then Professor B to C comparison. So I do the comparisons across each of the professors pairwise. I would calculate my theta. So I'm going to do this for one of these. So guys, for Professor A to C, I would have success as 279 divided by 165 divided by 225 divided by 191. So I would have 1.435. The next thing I would do is I would have the natural log of theta hat, and that's 0.36. Next thing I would do is calculate the standard error of the natural log of theta hat. That's 0.139. And the next thing I would do is calculate the test statistic. And that's 2.597. The 2.597 would be, let's see, statistically significant at the 0.001 level. It's kind of, you can see, well, back in the ANOVA, I think we ran into it. 3 asterisks stand for significant at the 0.001. To 0.01 and so on and so forth. So it turns out that the others, this is 1.089. This is 0.085, so I'm going to give you these so you can try it out on your own. 211. The Z is 0.402 according to, so we do not get statistical significance there. 1.318. 0.276, 0.211, and 1.308. So guys, remember these standard errors are different between there and there because we have different sample sizes. That's interesting to me that these are the same. I may have made a calculation error there, but nevertheless the Z is 1.308, so it's not statistically significant at the 0.05 level. So back to this relationship that we looked at first of all. I think the chi-square statistic turns out to be statistically significant. P-value is like 0.03, I do believe. You can test me on that one, which is less than 0.05. So we do get statistical significance, but just eyeballing it, I mean, what does that mean? And you don't know that stuff until you carry out the the process that that I've tried to teach in this video. Compare proportions, look at the odds, ratio, look at the natural log of the, or at least calculate the natural log of the odds ratio. And see the location in the distribution in which that test statistic lies. So, guys, it's extremely important here to realize that this test on the odds ratio does not duplicate the chi-square test. The chi-square test, at least in my opinion, is used to determine whether or not there is a relationship between the two variables. The z-test, as I've demonstrated, here, here, and here, is used to determine whether there's a particular association embedded within the relationships in the table. So, guys, this is a long video. I knew it would be, but gotta take the good with the bad, right? One of these days I'll upload a video that's going to be like 18 minutes long. So, guys, take care.